Hello everyone, welcome to Chem76A. Today we will begin chapter number 4. In this chapter we will learn about acids and bases. This chapter is divided into 5 sections. In section number 1 we will learn about definitions of acids and bases and we will discuss about Arrhenius definition as well as uh, Bronsted and Lowry definition. In next section, we will learn about the strength of acids, and the strength of acids is calculated from the acid dissociation constant pKa. So we'll talk about pKa values also, and then we will learn about equilibrium in acid-base reactions, and then in next section we'll discuss the uh, mechanisms of acid-base reactions, and finally in the final section we will discuss what are Lewis acids and Lewis bases. Okay, so let's begin this chapter by learning various definitions of acids and bases. Chemical terms such as anions, cations, nucleus, protons may be unfamiliar to most non-science people, but acid has found a place in everyday language. Commercials advertise the latest remedy for heartburn caused by excess stomach acid. Wine lovers already know that sometimes wine tastes sour because its alcohol has turned into acid. So acid is familiar to almost everyone on this planet. The name acid came from the Latin word acidus, uh, which means sour. This is because when tasting a compound was a routine method of identification, all of these compounds were sour. So those compounds were categorized as acids. So this is one general property of acids. They all taste sour. In this chapter, our study of acids and bases will serve as an introduction to the role of electrons in ionic reactions. An ionic reaction is a reaction in which ions participate as reactants, intermediate, or products. These reactions represent almost 95% of the reactions covered in this textbook. So in order to prepare ourselves for the study of ionic reactions, it is extremely important to be able to identify acids and bases. In this chapter, we will learn how to draw acid-base reactions and how to compare the acidity and basicity of different compounds. The first useful definition of acids and bases was put forward by Swan Arrhenius. So this definition is known as Arrhenius definition of acids and bases. According to Arrhenius, an acid is a substance which, when dissolved in water, it will produce H positive ions. So this was the original definition of acid put forth by Arrhenius. And according to the same definition, a base is a substance which, when dissolved in water, will produce hydroxide ions. Today, we know that it is not accurate to refer to an acid uh, as a substance which give rise to simple H positive ion, because H positive ions in water immediately uh, join together to form hydronium ion. So according to the modified definition of acid, or in other words, according to modified Arrhenius definition of an acid, a substance which produces hydronium ion in aqueous solution is known as acid. No change in the definition of base has been made because it's still the same definition. A base is a substance which produces OH ion in aqueous solution. In 1923, Danish chemist Bronsted and English chemist Laurie uh, independently proposed a new definition of acids and bases. Now the question is why there was a need for new definition. The reason for proposing a new definition is or was that previous definition, that is Arrhenius definition, did not cover all acids and bases. For example, we know, or it was known, that ammonia is a base. Uh, but according to Arrhenius definition, any substance which is a base must produce OH, or hydroxide, and but ammonia does not have hydroxide. So this reason, because of this reason, ammonia does not fit uh, in Arrhenius definition of acids and bases. Similarly, there were many other acids also which did not fit in under the definition proposed by Arrhenius. That's why new definition was proposed by Bronsted and Laurie. Now, Bronsted and Laurie definition is based on the transfer of H positive ion, and H positive ion is also known as a proton. Now, why it's known as a proton? Because hydrogen, neutral atom of hydrogen, contains one proton in the nucleus and one electron around it. So when hydrogen loses an electron, so loss of electron, it becomes H positive. So if we think about it, now from the neutral atom, the electron is gone. So what is left? So only proton is left. That's why H positive is also known as proton. So therefore, Bronsted-Lowry definition, we also call this definition is transfer of proton. According to Bronsted and Lowry definition, an acid is a substance which donates a proton. Now remember, although we are saying it donates a proton, but we refer proton to be H positive. And similarly, base is a substance which accepts a proton. In this chapter, we will primarily focus on Bronsted and Lowry definition of acids and bases. At the end of the chapter, we will briefly discuss Lewis definition of acid and bases also, but most of the time in organic chemistry, we consider acid and bases according to Bronsted and Lowry definition. Let's see one example of acids and bases according to Bronsted and Lowry definition. So consider a reaction between HCl and water. And let me so when we mix HCl in water, we know that we will get Cl negative plus hydronium ion. So let's check what happened in this reaction. So in this reaction, we can see that a hydrogen was transferred from high HCl to water. So in other words, HCl has given away its H positive. So this is a proton donor. So if HCl has donated a proton, another substance must have accepted it, and we can see water is the substance which has accepted the proton. So this will be a proton acceptor. So according to definition, any substance or any chemical which donates a proton is an acid. So therefore HCl is an acid, and um, water is a base. In the beginning, I mentioned that ammonia is a base, but Arrhenius' definition does not explain why ammonia is a base. Let's see if Bronston-Lowry definition uh, is capable of explaining why ammonia is a base. So ammonia, when we dissolve ammonia in water, or when we mix ammonia in water, or even with HCl, right? So we will get in aqueous solution. So we will get NH4 positive and Cl negative. So now we can clearly see that hydrogen is donated by HCl. So this is a proton donor. So hence it's an acid. And ammonia is a proton acceptor. So therefore ammonia is a base. So Bronston-Lowry definition does explain why ammonia is a base. In Bronston and Lowry definition of acids and bases, when an acid donates its proton to a base, the acid is converted to its conjugate base. So for example, if we write a reaction in which HCl donates a proton uh, to water, and water accepts it. So after donation, the leftover part, this part is known as conjugate base. So conjugate base is the species formed from an acid when it donates a proton to base. So in this case, HCl is donating the proton and leftover part is Cl negative. So Cl negative is now known as a conjugate base. Similarly, conjugate acid is the species which is formed when a base accepts a proton. So for example, if we write the same reaction, so HCl donates a proton to water, and water becomes hydronium ion, and HCl, leftover part of HCl is Cl. So water is accepting a proton, so therefore water is a base, and after accepting a proton, the new species which is formed, so this new species is known as conjugate acid. So in other words, after donating a proton, acid becomes conjugate base, and after accepting a proton, base becomes conjugate acid. So the relationship between acid-base conjugate pairs are represented in this reaction. In this reaction, we can see that HCl is donating a proton to water. So therefore, HCl is a proton donor, hence it's an acid, and water is a proton acceptor, hence it's a base. Now, after donating the proton, the leftover part is Cl negative, so this is the conjugate base of HCl. And after accepting the proton, the new species formed is the hydronium ion. So hydronium ion is the conjugate acid of water. It should be noted that Bronsted and Lowry definition does not require water uh, as a reactant. For example, ammonia uh, is reacting with acetic acid in this case. So proton is being transferred from acetic acid to ammonia. Therefore, acetic acid is a proton donor. Hence, it's an acid, and ammonia is a proton acceptor. Therefore, it's a base. And after donating the proton, the acetate ion is the leftover part from the acid. So hence acetate ion is the conjugate base of acetic acid, and ammonium ion is the species formed from ammonia after accepting a proton. So hence ammonium ion is the conjugate acid of ammonia. We show the transfer of protons from an acid to a base by using a curved arrow. For example, if we have an acid-base reaction as shown here, we can see in this reaction that uh, proton is being donated from the HCl to water. So therefore HCl is the proton donor, and as therefore it will be an acid. And water, because it's accepting the proton, so therefore water is acting as a base. To actually show how this transfer has taken place, we must write all the acid and base structure in their correct Lewis forms. So in other words, we need to write all the lone pairs and all the bond pairs correctly as represented in Lewis structures. And then we use curved arrow to show the change in position of electron pairs during the reaction. It is important to notice here that we show the change in position of electron pairs. The tail of the curved arrow is located at an electron pair. So although we are gonna show that the proton is being transferred from here to here, but when we show the mechanism, the curved arrow is shown such a way that the tail end of the arrow is at an electron pair. So for example, a lone pair in this case, and the head of an arrow is pointing towards the proton. So you can imagine that the electrons are grabbing the proton rather than it's being donated, is taken away, if that helps. And we must indicate where all the electrons are going. So if the proton is transferred or is taken away by the oxygen atom of water, then this pair of electron in the bonding site, so this will move to the chlorine atom, and the resulting conjugate uh, acid and conjugate base are shown here. The arrow which originates from the lone pair and goes to the proton, so this arrow indicates the formation of a new bond. So this is a new bond formation between oxygen and water. And the arrow which indicates the bond pair of this bonding pair of electron going to the chloride ion, so that indicates the breaking of this bond. So thus in the reaction of HCl and water, a proton is transferred from HCl to water, and in this process an OH bond is formed, so as shown here, and an HCl bond breaks. It is important to keep in mind that arrows indicate movement of electron, not atom. So in other words, if we show the process in this way, so this is incorrect. So these curved arrows do not show the movement of atoms. So therefore this is incorrect. So the correct way is that we always show the movement of electrons, which electrons are moving to create a bond and which electrons are moving to break a bond. All the Bronsted and Lowry bases we have discussed so far, they have only one side that can act as a proton acceptor in any acid-base reaction. For example, water has only one side, which is this oxygen atom. So that's the only place which can accept a proton. Uh, and similarly, ammonia has only one nitrogen atom which can accept a proton. However, many organic molecules have two or more sites that can act as a proton acceptor. Although there are many different kind of compounds which may have multiple proton acceptor sites, but we will concentrate mainly on carboxylic acids, esters, and amides. Let me explain with the help of an example. So imagine we are performing an acid-base reaction in which we are reacting a carboxylic acid group uh, such as acetic acid with a strong acid, uh, maybe sulfuric acid. So in this case, now in carboxylic acid there are two sites where proton can be accepted. So one of the site is the carbonyl oxygen here, and the other site where proton can be accepted is the hydroxyl oxygen. So it means this reaction uh, may result in two different products. So let's consider both of them. So let's first take a look at what happens when the carbonyl oxygen accepts the proton. So in this case, I'll refer it to the green case, and I'll draw it with the help of green arrows. So this carbonyl lone pair will be used to create a bond with the new hydrogen or new proton, and the end result will be uh, a conjugate acid where the carbonyl oxygen will have an additional proton connected to it and a positive charge. The rest of the molecule stays as such. Now, because carboxylic acid is accepting a proton, therefore carboxylic acid is acting as a base. So this intermediate, I'm gonna call this intermediate A. So this intermediate A, or this species A, is a conjugate acid, and of course the conjugate base of sulfuric acid will also be there, which is HSO4 negative. That's one possibility. The other possibility is when the oxygen from the OH group, that oxygen is the site where the proton is acceptor. So in this case, the lone pair from the OH oxygen will be used to create the bond with the proton, and in that case the end product will be a formation of a species in which the hydroxyl oxygen will have an additional proton and a positive charge here, and of course we will have a conjugate uh, base of sulfuric acid. So let's call this species B. Now the question is, which species or which site is the true proton accepting site? Do we have 50-50 probability of getting both of these species A and B present, or one of them is preferred over the other one? The answer is one of the species will be preferred, and the species which will be preferred is the one where the favored site is the one in which the charge is more delocalized. Now what do I mean by that? So if we look at both A and B, we will see that oxygen has a positive charge, one of the oxygen. So in A, the carbonyl oxygen has a positive charge, and in B, the uh, hydroxyl oxygen has a positive charge. Now oxygen is uh, pretty highly electronegative element, and oxygen would not like to have a positive charge on it. That makes oxygen less stable. So if this charge is delocalized or dispersed by some way, then that species will become more stable. So in other words, in whichever case, whether it's A or B, whichever is capable of delocalizing this charge, that species will be preferred. If the positive charge is dispersed or delocalized better in A, then A will be the favored product. If the charge is delocalized in species B, then B will be the favored. So let's investigate both of these species separately and see which one is more capable of delocalizing the charge. Let's consider the species A first. So species A had a positive charge on the carbonyl oxygen. Now we can write the resonance structures for this one. So this pi electron will go, we use different color. So this pi electron can be used to stabilize the positive charge, and because now the pi bond is gone, so therefore this carbon will get a positive charge. And we can write another resonating structure in which there is a double bond between the oxygen and carbon. So because oxygen has donated its electron, that's why oxygen has a positive charge. So as you can see that the original positive charge, which was here to begin with, it has now dispersed, or it has spread over three different atoms. One oxygen in the second structure, let's call this A1. this would be A2 and this would be A3. Okay. So in A1, charge is on oxygen. In A2, the positive charge is on carbon, and A3, it's again on the other oxygen. So the charge is well delocalized. Although these three resonance structures look equivalent, or they look equally contributing, but there are few factors which we must consider. So in A1, all octets are complete. So it means both oxygens and carbons, their octets are complete. However, in the A2 structure, this carbon octet not complete. So for the carbon, so this carbon octet is not complete. And again in A3, octets are complete. So all of them. So therefore A2 is less contributing than A1 and A3, because octet of carbon is not completed, so therefore it's less significant. So therefore we can say that A1 and A3 make greater contribution to the resonance hybrid because they have completed octets, and A2 does not contribute much, but it's a structure. So we can say that in this case we have three contributing structures, in which two structures contribute more, which are A1 and A2, and the third one does not contribute much. So it means that in species A, the positive charge is delocalized over three atoms, with greater share of the charge is shared by two oxygens. Carbon doesn't pitch in much, it doesn't share that much, but still it contributes a little bit. Now let's take a look at species B. So as we remember, in case of the product B, the positive charge was on the hydroxyl oxygen, and this oxygen was connected to two protons. Now in this case, we can write one and only one structure, resonance structure. Now this is not possible. Why it's not possible? Because oxygen already has a positive charge. It cannot afford to lose any more electron, and donating this will mean that oxygen is losing another electron. So that does not happen. If it already has a positive charge, it's gonna hold its lone pair tightly to itself, so it's not gonna donate. So that's not possible. Okay. Now these lone pairs cannot move here, because lone pairs only move to the neighboring um, bond. So only possible resonance structure is if this pi bond moves here, and the resulting structure would be this one. Let's call this B1 and this is B2. So in case when hydroxyl oxygen is acting as a proton acceptor, we can only write two contributing structures. Now B1, octets are complete. However, in B2, there are many problems. So first problem is carbon octet not complete. Second is So that's a one strike. The other strike is uh, there are separation of charges. Uh, when we have multiple charges in the same molecule, that is highly uh, energetically inefficient, or in other words, it makes a molecule extremely unstable. And the third and most important is same charges on adjacent atoms. So same or similar charge on adjacent atoms. So positive right next to each other makes it extremely unstable. Because of all these negative properties of B2, the resonance contribution of B2 is negligible, as if it doesn't even exist. So what do we conclude now? So we can conclude that in case of species B, where the hydroxyl accepted the proton, that does not uh, delocalize the positive charge that well. In fact, it doesn't delocalize at all. On the other hand, when the carbonyl oxygen acted as a proton acceptor site, we had three contributing structure, although one of the structure was less than the other two, but at least we had three structures. So therefore, we can conclude that the species A was better, because in species A, the positive charge was delocalized more efficiently on three different atoms, and in species B, the charge does not get delocalized. So therefore, we can say that uh, in case of carboxylic acid, the protonation mainly occurs on the carbonyl oxygen only. Let's take a look at this problem. Does proton transfer to an amide group occur preferentially on amide oxygen or the amide nitrogen? Now this problem can be answered by applying the same concept what we learned in case of carboxylic acid. Amide group, as we know, has a carbonyl part and a amine part. So the amide group is CONH2. So now this problem is asking that if uh, we have some amide and it accepts a proton from any acid, let's take a generic acid HA, then will that product be this one, in which the oxygen act as the uh, proton acceptor site? Let me use different color again. I'll call it the blue case. So in this case, the oxygen will be the proton acceptor site, and it will get a positive charge, and of course we will get a conjugate base of that acid. Or the second possibility is that the nitrogen acts as the uh, proton receiving site. So in that case, nitrogen will get the positive charge. So let's again call this the first one species A and the second one to be species B. So again, we need to determine if the A is the preferred species which is formed, or in other words, is oxygen is the preferred site where proton is accepted, or nitrogen. So again, we can answer by looking at how well the charge is delocalized. So in case of A, we can write resonance structures. So let's call this A1, and the next structure would be where carbon gets the positive charge, and then the third structure is the one where nitrogen gets the positive charge. So this would be A2 and this would be A3. In A1 and A3, they all have complete octets. However, in A2, carbon octet is not complete. This carbon. So therefore A2 is less contributing, but still we have three contributing structures. So positive charge is delocalized over three different atoms. It's delocalized over oxygen and then carbon and then finally on nitrogen. So charge is well dissipated. Now if the protonation occurs at the nitrogen atom, so then we will get the species B. So in that case, we can only write one additional resonance structure, and in that resonance structure we will see that we have a lot of destabilization issues. So let's call this B1 and this would be B2. B1 is okay, all octets are complete. However, B2, we have separation of charges, too many charges. That's what I'm trying to say. And similar charges on neighboring atoms, carbon. So carbon and nitrogen have same charge right next to each other, makes it extremely unstable. Carbon octet is not complete. That also makes it extremely unstable. So the contribution from B2 is negligible. So we can almost cancel it. So in case of B1, species B, only one contributing structure exists. For species A, where oxygen act as a proton receiving site, we have three contributing structure. So in B, the positive charge is not delocalized. So therefore, we can conclude that the proton transfer in case of amides occurs mainly at carbonyl oxygen, because that's where we get more delocalization of positive charge and hence we have a more stable cation. So far we have considered proton transfer to atoms which have a lone pair of electrons such as oxygen or nitrogen. Uh, Proton transfer reaction can also occur with compounds containing pi electrons. The examples of such compounds are alkenes and alkynes. Now, for example, in case of an alkene, let's say a butene, we will learn alkenes in more detail in chapter 6 and 7. But for now, just remember the compounds where we have a double bond, they are known as alkenes. So this pi bond can also act as a site where proton can be accepted. So when alkenes react with a strong acid such as HCl, HBr, HI, or sulfuric acid, uh, it will accept a proton where pi electron are used to create a new bond with the proton, and the resulting product is let me use a different color. This resulting product will have a carbon atom with a positive charge, and this species where carbon atom has a positive charge are known or is known as carbocation. So when pi electron act as a site to receive a proton, it will result in formation of a carbocation. In carbocation, the carbon atom which has a positive charge will have only 6 electrons in its valence shell. We will study carbocations in detail in chapter number 6. Uh, but for now, just remember that pi electrons can also act as a site to receive a proton in acid-base reactions.